Assalamualaikum and hi. We would like to present about cyclic group topic in algebra structure. Hi, my name is Nur Aina Farhana binti Rosli. My student ID 2020819872.
Hi, my name is Nurin Jazlina binti Azlisha. My student ID is 2020819644. To prove this theorem, for the first step, we must define what is subgroup and what is cyclic group. We start by define cyclic group. We let G be a cyclic group generated by A, where we can write the entire group like this, which is A power of n, where n element of all integers. Next, we define subgroup. We let H be a subgroup of G, and we can just denote it as H is less than or equal to G. Now we are trying to prove that every subgroup of this group is cyclic. Our goal in this part is we need to show that H is a cyclic in two cases, which is trivial and non-trivial cases. For trivial case, subgroup H is an identity element. We know that the subgroup of an identity element is the trivial subgroup of G and always a subgroup for any group we have. So, if H is a trivial subgroup, then the identity element is its own generator. So, it is proven that H is a cyclic. Next, for non-trivial case, we assume that H is not trivial case. So in this case, we will have non-trivial element, and we call it as non-trivial element X is an element in H and also in G. From this, we can tell that X is equal to A power of n for some n where it is an element of integer. We let m be the smallest positive integer such that a to the power of m belongs to H. We let b equal to a power of m. So now we are going to claim that our subgroup H can actually be generated by this element a to the power of m, where it is equal to b. So it can be generated entirely by this element b. To prove our claims that H is cyclic, we need to show that any element in subgroup H can be written as a power of element b. Let's say C is any element in subgroup H, and we can write C equal to the a power of x for some integer x. We will use the division algorithm to show that a subgroup H of a cyclic group G is a cyclic. So we can see that there exist unique integers Q and R such that we can write X equal to M times Q plus a remainder R, where we have R is greater than or equal to 0 and less than m. We can rewrite our element of C equals a to the power of x, which we can write a to the m times q plus r, and we can rewrite this where we have a power of m times q plus r. We call that inverse a to the m to the negative of Q and multiply this inverse to the both side, we will get like shown at the slide above. The reason why we are doing this is to show that in fact A to the R is an element in H. Let R must equal to 0. So we can tell that A to the X is equal to the A to the M times Q. From this, we can see that H is generated by B, since we took any arbitrary element C in our group H, ensure that it had to be A power of B. So our proof is cyclic. Next, this is example for theorem 1. Find all the subgroup of integer modulo 12. First, we list the element of integer modulo 12, which is 0, 1, 2, 3 until 11. Then, let group of integer modulo 12 under addition is cyclic. Then the subgroup of integer modulo 12 are also cyclic. Subgroup are in one-to-one correspondence with the divisor of 12. So the divisor of 12 are 1, 2, 3, 4, 6 and 12. We will construct a table under addition for integer modulo 12. There are 6 subgroups that are generated by 0, 1, 2, 3, 4 and 6, and notice that every subgroup there will be an identity element. Then we will identify the element of every subgroup that generate by 0, 1, 2, 3, 4 and 6 by using addition table for integer modulo 12. So the first subgroup, which is generated by 0, it will only be the identity element. For the second generated by 1, it will be identity element 1 times 1, 1 times 2, 1 times 3 and so on. Next, generate by 2, which is 1 times 2, 2 times 2, 3 times 2 and so on. And it will be the same until the last subgroup, which is generated by 6, which will be identity element 1 times 6, and that's all.
Proposition Theorem 2. If G is a cyclic group, we add odd number of generator, then modulus of G equal to 2. Given that G is a cyclic group with odd number of generator, if order of G is infinite, G is an infinite cyclic group. Then G is similar to integer group under addition. And we all know that integer group under addition has only 2 generators, which are -1 and 1. That means even number of generator. Thus, this can't be the case considered. Therefore, taking G to be a finite cyclic group. Now, for any finite cyclic group G, the number of generator of G is V times n. Therefore, for odd number of generator has to be 2. Thus, for a finite cyclic group with odd number of generator, the group has only V times 2 generator. This directly conclude that G is isomorphic to integer modulo of 2 under addition. Hence, modulus of G equal to 2. Let G equal to P equal to set of P power of B, and B is element of integer, be an infinite cyclic group, and let Q element of G be another generator of G, so that G equal to Q set of Q power of B, and B is element of integer. Since Q element of G equal to P and Q equal to P power of n for some B element of integer. Similarly, since P element of G equal to Q and A equal to Q power of A for some A element of integer. Then P equal to Q power of n equal to P power of B times A equal to P power of BA. Thus, P power of AB equal to P implies P power of AB times P inverse equal to P times P inverse implies P power of AB minus 1 equal to exponent equal to P power of 0.